In this video we'll be making a very basic version of the spine. In particular we'll be looking at getting good rotations from the spine. To do this we'll need to overcome certain limitations which come from the curve solver. We'll start by building a very basic spine. In the scene we have a geometry node called basic spine, and I'm going to enter this. To create our base geometry we'll get a line node. We'll of course need to be able to convert everything to joints, so I'll get a couple of rig doctor nodes. In the first rig doctor node I'll set the name to be spine. This is for the joints that will constitute our spine. In the second rig doctor node I'll set the name to be CTRL, and this will be for our controls. Both of the nodes can then be selected, and I'll turn on initialize transforms. I can then connect the lines to these nodes. We'll want more detail in the spine, and we'll add this with the resample node. I'll set this node to use maximum segments, and I'll turn off maximum segment length. I'll set the segments to 7. I do not currently have enough detail for my controls. We'll get this by changing the line node directly, where we'll set the number of points to be 4. I'll add some control geometry with an attached control geometry node. The control geometry needs a name attribute, so we'll get a name node, and I'll set the name to be box. I'll then set my geometry with the box node. To control the rig we'll need a rig pose node. I'll need to attach my controls. I'll add one attachment. I'll use an asterisk to specify all points, and these will be connected to the box. The box is a bit large, so I'll select it and change the uniform scale. We should now be able to control our joints with the pose node. However, I'm not happy with the current hierarchy, so I'll get 2 reparent joints nodes. I'll add one reparenting operation to the first node. I'll select all the joints as children and leave the parenting empty to make sure that there is no parenting. In the second reparent joints node we'll want 2 operations. The first operation will make control 0 the parent of control 1. The second operation will make control 2 the child of control 3. The rig pose node should come after the parenting, so I'll rearrange the network. I should now have a top control, and this should have a child which will be used as a tangent. The bottom control should have a child which is also used as a tangent. Next we'll need to add the solver. For this we'll need a rig attribute VOP node. The spine will plug into the first input, and the controls will plug into the second. I can then enter the VOP, and we'll get a curve solver node. We'll need to set our transformations, so I'll get a set point transforms node, and I'll connect these nodes. First I'll connect the points, then the transforms, then the local transforms. This by itself should be enough to set up a very basic skeleton. With the pose node I'm going to turn off some of the displays. I'm going to right click in the viewport and turn off the display joints and display joint axes. So what we have here is a basic spine with some basic spine controls. At this point everything looks fine, but we actually have problems. And we're now going to look at what those problems actually are. I'm going to select the rig attribute VOP, but I'm not going to enter it. I'm going to open the information menu instead. We have quite a few point attributes that have been created by our rig doctor node. In this case I want to use the transform attribute. I'll click on it to activate the visualizations. I'll then right click on the visualization menu to open up the contextual menu. I'll look for the transform parameter, and I'll click on the pencil icon to edit this visualization, and I'll turn the scale length down to 0.1. This will make it easier to see the transform visualizations clearly. I can now re-enter my solver, and we can update some of the parameters. I'll want to set the transform to match what they originally were, so the look at axis will be set to Y, and the look up axis will be set to -Z. I'll then lock this parameter menu so we can examine some of the problems we've got. I'll select the tip control and I'll move it, and the problems should be obvious immediately. These transforms are pretty horrible. Even the slightest movement will cause the joints to flip. So I can try changing the twist mode. First I'll change the mode from angle to default, and this in no way solves the problem. We can change it to quaternions, which will generally give better rotations in these kind of situations, and initially it looks like we've got a better transformation. However, the moment I pass the y-axis, we get flipping again. This will apply to every single one of these twist modes. And the twist mode, clamped angle and angle are actually worse, as you need to understand how they work before you can even use them. There's also very little information in the manual about these options. So what we actually are going to do is ignore these rotations entirely. One of the things which makes Houdini very powerful is that we're given a lot of low-level control, and KineFX gives us this level of control when it comes to rigging. So we'll set the twist to none, and we're going to create our own transformations. With no twist set, we have a far more consistent result, although the control's rotation no longer affects anything. We'll be creating our own rotations, and we'll be using a linear interpolation for this. This technique could easily be converted to using quaternions, and this would allow us to use spherical linear interpolation instead. But to understand how it works, it's far easier to work with simple linear interpolation. We'll now be setting our controls. We'll not be doing it with any of the solvers in the rig attribute VOP. Instead, we'll be setting them in Vex with the wrangle node. The information we'll need is the rotation of the tip control and the root control. So we'll need to get the transform of this control here, which is our tip control, and we'll interpolate between this transform and the transform of the root control, which is this control here. We'll use this information to recreate all the transforms along the curve. To start, we'll get an attribute wrangle node. Our spine will go into the first port, and our controls will go into the second port. We can take a look at the control joints. I've added a visibility node here to hide the controls, and we can take a look at the point numbers. What we'll need is 0.0 for the first control and 3 for the last control. Of course, in a full rig we'd need to be more precise here, but in this case I only need these point numbers. So I'll start by getting the transform for the points. These transforms will be a rotation matrix, and for this we'll set these as a matrix 3. Here we need to make sure that we don't accidentally specify the wrong size of matrix. I'll call this first matrix root, and we'll set this using the point function. This will give us a point attribute. We'll need to specify which input we're getting it from, and in this case this is the second input, so here the input number will be 1. The attribute name is transform, and in this case the point I'm going to be getting it with is 0.0. Next comes the tip control. This will also be a matrix 3. I'll call the variable tip. It will be set with our point attribute. We'll specify the second input with input 1. The attribute will be transform, and the point number here will be 3. The final information to get from the rig is the transforms for the spine joints. This will be a matrix, and I'll call it spine. This will be set with our transform attribute. We'll specify that it is a 3x3 matrix with a 3. There's an attribute using the @ symbol, and the name is transform. This is of course the transform attribute that we're currently visualizing in the viewport. At this point I'll check that I'm actually getting values by printing them to the console. I'll use the printf function. The values in the string that I want to print are root, tip, and spine. I'll need to add wildcards so we can insert our values into the string. For this I always use the wildcard %g. I'll then use a \n to specify that we have a new line. I can then pass in the values that I want to test. The first one will be root, the second one will be my tip matrix, and the third one will be my spine matrix. We can then run the script, and I get a printout, and I'm printing out my root and my tip, but not my spine. So there are two potential problems for the script. The first one is that I didn't paste down my wildcard correctly. This should be a percentage followed by g. The second potential problem is the setting of the spine transform. In many cases you'll need to use a set function to assign a value to a variable. That is, however, not applicable here. We can then print out our values and look at what we get. So we get multiple values printed out. This is because we're getting the values printed out for each point. For all of these, the root and the tip values are the same, and the spine values are different. We're getting all the information we need, so now we can proceed to add in some variables we'll need to work with. We'll need 3 vectors, each of which represents a direction. I'll call the first of these my x direction, and I'll set it to 1, 0, 0. I'll then duplicate this line twice. Next will come my y direction, and this will be set to 0, 1, 0. Finally, we have the z direction, and this will be set with 0, 0, 1. I'll then comment out the print statement because we don't need it at the moment. We can now start working on the logic of the script. The first thing that we'll need is a list of values that range between 0 and 1. In this case, we'll need a value that starts at the root point with 0 and ends at the tip with 1. To do this, we're going to create a float value. I'll call this variable range. Our first value will be the number of the current point, and we need to cast this value as a float. We do this with 2 parentheses, and we'll write float in these. We'll then add the attribute at pt_num. This will be divided by at num_pt, and once again this will be cast as a float. We need these to be float values because we are dividing. If we leave these as integers, we'll get truncated values of 0 and 1. Now this is a 0-based index, so we'll need to subtract 1 from the number of points. I'll place this in parentheses so that the division doesn't become ambiguous. We can then visualize these values. I'll add an attribute, and this should be a float attribute. I'll call this r, and we'll set this with the range value. I can now visualize the information. I'll bring up the information for the attribute wrangle node, and I'll click on the r attribute. We'll access the contextual menu for the visualizations, and we'll edit this value. I'll change the type to be a marker so that it will show up as text, and I'll set the text to be a purple. And you can see that we have a range of values. Our bottom point will have the value 0, and our top point will have the value 1. This set of values is exactly what we want. We do, however, need another set of values that runs in exactly the opposite direction. In other words, we want it to go from 0 at the tip to 1 at the base. The reason for this is we're calculating 2 transforms. We want the root transform to have a strong influence at the base of the spine, starting with completely controlling the first point, and we want this influence to fall off as we move up the spine. Eventually, when this reaches the tip of the spine, we want it to have no influence. Likewise, we want the tip to have its influence, and we want this influence to pass down the chain. By the time it reaches the bottom, it should have no influence. So I'm going to create another float value, and I'll call this one inverse. And we'll set this to be 1 minus the range value. I can then create a visualization for this as well. It's a float attribute, and I'll call it I. And I'll set this with the inverse value. We'll want to set the visualization for this attribute again. Once again, it should be a marker and not a color. And in this case, I'm going to set the color of the text to be red. We now have values that start at 0 at the tip and go to 1 at the root, and values that start from 0 at the root and go to 1 at the tip. So what we'll want to do now is we'll want to actually update our transforms. We'll create the algorithm to set up our transforms, and then after we've created that, we can update those equations to use interpolated values from our control points. I'll start by setting the value which points down the length of the bone. In this case, it will be my y direction. So my y direction will now be set with spine.yx, spine.yy, and spine.yz. So we've got our first value to set. This value can then be used to set the transformation matrix, which will allow us to see its influence. So we'll set our transformation matrix at the end of the script. It will be 3 for a 3 by 3 matrix at transform. and we'll set this with a normalized x direction, a normalized y direction, and a normalized z direction. I'll then turn off the extra visualizations for the range and the inverse. This will allow us to more clearly focus on the transforms. I've made a mistake here. The final value of the spine should be YZ and not ZZ. We're now setting the transforms explicitly again. We have our Y directions pointing along the curve, and we have a unit vector for both the X and the Z direction. To calculate a transform, you only need two directions. In this case, the first direction will be our Y direction. We'll then need a direction to serve as an up vector. This will eventually be our interpolated values. If we look at the root control, this X direction is what we'll be using to set our X direction for our points, and we'll be setting the directions at the top of the spine using the X direction from the tip control. So in practice, we'll treat these interpolated directions as our X direction, and we'll calculate our Y direction using them. So our Z direction will be equal to the cross product of our Y direction and our X direction. And we get a Z direction that far more closely matches our curve. We may need to swap the arguments in the cross product in order to reverse this Z direction, but we'll look at that later. We'll then want to create the X direction. This X direction will often end up different from the X direction used in the preceding cross product. Once again, this will be set with a cross product, and this will be set with the cross product of the Y direction and the Z direction. This will ensure that all of our directions are orthogonal, or basically that all the directions are perpendicular to each other. We now have a much better looking result, but this doesn't compensate for the twist. So now we want to interpolate between the x vectors of our two controls. So I'll need to extract the x vector from both of these controls, and I'll create two vectors to do this. We'll start with the root. This will be a vector. I'll call it rvec for root vector, and we'll set this from the root. The first value will be root xx, then root.xy, and finally root.xz. This will be followed by a vector for my tip. This will be a vector. I'll call it tvec for the tip vector. We'll use the set function for this, and we'll set tip xx, tip xy, and tip xz. So now we've got the x vector from both of the controls, and we can interpolate between the two of them. So we'll have a vector, and I'll call this vector out. We'll now calculate this vector, but I'll turn on my visualizations to make this calculation easier. In this case, the visualizations that I want to turn back on are the range and the inverse. And I'll need to fix some spelling errors. Tip should be spelled with a capital T. It does not matter which order you calculate these in, but I will start with the root. And I want the root to be multiplied by a range which starts with 1. This means I'll be multiplying the root by the inverse. We'll place this in parentheses, so we'll have rvec multiplied by inverse. This will then be added to the results of tvec multiplied by range. So now we can change the setting of the y direction. Instead of using the x direction in the cross product, we'll use our out value. Before we look at the results in the rig, we'll update the visualizations. This will allow us to see what our out equation is actually doing. I'll call our test attribute O for out. We can then turn this visualization on, and the visualization should be set to a marker, and I'm going to set it to be a vector. We haven't yet added a proper value to set the vector to. This should be set to the value of out, and it should be normalized. When working with transforms, we always want normalized values. Here I've made another error. I forgot to specify that this attribute should be a vector attribute and not a float attribute. We should now see the result of our out equation, and we're getting an interpolation of the x vector from the root to the tip. We're then getting a cross product of this value to work out our z vector, which gives us a vector perpendicular to the y direction, And then we calculate the cross product again to give a vector which is perpendicular to those two. In this case, we want z to be facing in the opposite direction, so we'll swap the arguments of the cross product around. The directions were originally facing in the same direction as the controls, and now they're matching again, and this is the result which I wanted. This is not a perfect solution, and we could probably get slightly better results using quaternions. We will probably still get some flipping, but this should only occur at a more extreme angle. An advantage that we have with this kind of approach, however, is we have more fine control over the transformations themselves. For example, it would be very easy to update this so we could set the interpolation with the ramp parameter. I'll now zero out the controls so we can test if it is working properly. Basic movement of the spine is no longer causing flipping. Moving the tangent isn't creating problems either. And I'm getting reasonably smooth interpolation when I'm rotating to the side. I can test my rotation to see the extent of the rotation. I do get flipping. If we take a look at point 4, we'll see that we get flipping at about 180 to negative 180 degrees. This should give us a decent range of rotation, and we're getting a decent interpolation within this range. And now we should have basic controls with a much better interpolation of the spine.